All right, today we're going to dive into something really cool, a framework that tries to build a whole universe from just a few simple ideas. It's called the Unified Postmodern Theory, or UPT. Let's get right into it.
So just imagine for a second, what if you could lay down a couple of basic rules, and from just those rules, everything else, everything, movement, change, even complex things like waves, just naturally falls into place? Well, that is the incredibly ambitious idea behind the UPT framework we're looking at.
Okay, so first things first. Before you can have rules, you need a playground for them to work in. The theory starts by defining its own little world. Everything that happens inside a very specific physical boundary. The UPT calls this the domain of ownership. Think of it as our own little self-contained universe for this thought experiment.
Now, inside this universe, we really only have three main characters in our story. First, you've got I, the mass intensity. This is literally all the stuff in the system. Then there's E, the state energy. That's pretty straightforward. It's just the total energy of all that stuff. And finally, we have mu, the state potential. This one's the real mover and shaker. It's the force that actually drives all the change. The entire story of this universe flows from how these three interact.
So, how does any of this stuff know what to do? Where does it get its marching orders? Well, in UPT, it all comes down to one thing: energy. The total energy of the system is basically the complete instruction manual, the blueprint for everything that's about to happen.
Okay, so let's zoom in and look at the energy at any single point. This equation might look a little intimidating, but the idea is actually super intuitive. It has two parts. The first part, the alpha I, that's just the energy you get for having stuff there in the first place. Simple enough. But the second part is the really clever bit. It's about how that stuff is arranged. Think of it like this. It costs energy to have a really crowded area right next to a totally empty one. The system prefers things to be smooth.
And to get the total energy of our entire system, E, well, you do exactly what you think you do. You just add up that energy density from every single point inside our boundary. That's it. This one number, E, tells you the complete story of the system state at that very moment.
So we have our energy blueprint. We know the state of the system. But, a blueprint just sits there. What's the spark? What actually pushes things to happen? That is where our third key player, the state potential, finally enters the stage. And I love this intuition the theory gives us. Think of mu, the state potential, as a kind of internal pressure. It's just like the air inside a balloon. Wherever the pressure is high, it desperately wants to push outward towards where the pressure is low. This pressure, this is the engine of all change in the system. And get this isn't just a nice little metaphor. This internal pressure is mathematically born directly from the energy equation we just looked at. It's not some new rule we're tacking on. Nope, it's a direct consequence of the energy blueprint itself. And that's a core idea here, how elegantly everything is interconnected.
All right, let's do a quick recap. We have the stuff, that's I, we have the energy state of that stuff, E, and now we have the pressure that wants to make things happen, mu. So with all the pieces on the board, we can finally write down the rules for how things actually move. And what's kind of amazing is that there are only two rules that govern everything. Just two. The rule on the left describes what happens inside the system. And it says exactly what you'd expect. Stuff moves away from high pressure and flows towards low pressure. Makes sense, right? The second rule, on the right, is for the boundary itself. It says the boundary will also shift and move around, and it will always do so in a way that tries to lower the system's total energy.
So, we've got a system that's completely defined by its energy, and we have two simple rules for how it moves to try and lower that energy. Now, what happens when you put those two ideas together? Well, you get the single most important, most profound consequence of this entire framework.
The logic to get there is actually beautiful in its simplicity. You just start by asking a basic question. How is the total energy, E, changing over time? And then all you do is plug in those two rules of motion we just saw, the one for the inside and the one for the boundary.
And boom, this is what falls out. The rate of change of energy, dE over dt, is always less than or equal to 0. Let that sink in for a second. What this means is that in this self-contained universe, the total energy can only ever go down, or at best, stay the same. It can never, ever increase on its own.
So what does that actually mean for our system? It means the system is fundamentally lazy. It has this built-in, completely unavoidable drive to settle down. It's always going to rearrange itself to find the lowest possible energy state it can. It's like a ball rolling downhill and settling at the very bottom of a valley. And once it gets there, once it can't lower its energy anymore, it becomes stable, and everything stops.
But okay, a system that just rolls to a stop is, well, it's kind of boring, right? What happens if you take that stable system and you give it a little poke? This is where things get really interesting, because some incredibly powerful phenomena pop right out of those simple rules.
So yeah, let's ask that question. Let's say our little universe is sitting there, perfectly content at its lowest energy, and we just nudge it a tiny bit. What does the theory say is going to happen next?
To figure that out, we get to use a pretty cool mathematical tool called linearization. You can basically think of it as a superpowered magnifying glass. It lets us completely ignore the big, stable system and zoom way in to focus only on those tiny little disturbances, those little ripples on the surface.
And when you apply this magnifying glass to our original rules of motion, this is what you find: a wave equation. Now, this is a huge deal. You see, we didn't add waves to the theory. We didn't write a special rule for them. They just appeared. They are a natural, built-in property of the system's DNA. The system is literally hardwired to make waves.
And it's not just waves. The whole framework is beautifully self-contained like this. The fact that mass is conserved, it's baked in from the very beginning. The theory provides crystal clear rules for how boundaries should behave. It can even predict the speed of those waves and how they fade away. All of it emerges from that one initial idea about energy.
And this all culminates in what's called the closed system theorem. It's a really important special case. It says that if your system is totally isolated, meaning nothing is leaking in or out and the boundary isn't being pushed or pulled, then that tendency for energy to decay stops. Instead, the total energy E is perfectly conserved. It's the other side of the coin. When a system is truly on its own, its energy stays constant.
So that leaves us with one final big idea to chew on. This theory paints a picture of a universe where the energy state right now completely dictates the entire path forward, all because the system is just trying to find a lower energy state. So if a system's entire future is just a consequence of its present energy, what does that say about the nature of cause and effect? Something to think about. Thanks for joining me on this one.